Hello everybody. So I'll be presenting my presentation on lab report number 5, and this is a hands-on look at Kirchhoff's rule, one of the most fundamental ideas in electricity and circuit design. So in this experiment, we tested two big conservation laws. Kirchhoff's junction rule, which says that the total current entering a junction equals the total current leaving it, meaning electric charge never disappears, and Kirchhoff's loop rule, which says that when you travel around any closed circuit, the total voltage rises from the battery equals the total voltage drops across the resistors. These rules are the reason lights don't dim when you plug in your phone and your computer at the same time. The energy simply divides among the components without being lost. And our goal was to collect current and voltage data from each resistor, verify both rules mathematically, and compare our experimental results to theory. And I'll be talking about the setup a little later and our step-by-step procedure, the recorded data, and finally the analysis that shows just how accurate these laws really are. Moving on to materials. Here's what we use to build our circuits. So a Pascado DC power supply is set to 7 volts DC with a 10 volt limit and a 1.1 amp limit. Four resistors labeled R1 through R4. We measured each one with a digital multimeter and marked them with tape so we wouldn't mix them up. And one voltage sensor and one current sensor, both connected to the Pascal interference. Um, a breadboard and connecting leads. And finally, the capstone software set to show the reading in digits or mode against in digits mode instead of graphs. So no new equipment was introduced for this lab, but this was our first time using the digits display, which helped us capture stable voltage and current values in real time. Everything was powered by the same Pascal interference that handled both sensing and data collection. Moving on to procedures, we started off by carefully checking each resistor using a digital multimeter. This step was really important because even small changes in resistance could throw off our current and voltage readings later on. Once we had the values, we labeled each one clearly as R1, R2, R3, and R4 using small pieces of tape just to stay organized and make wiring easier. So after that, we began setting up our circuit according to the lab diagram. On the top branch of the circuit, we placed resistor R1. On the bottom branch, we connected R2 and R3 in series, meaning the same current flows through both of them. Those two branches then rejoined and passed through resistor R4, which was connected in series before returning to the positive terminal of the power supply. Next, we set up our Pasco DC power supply. We switched it to DC mode and set the voltage to exactly 7 volts, keeping the voltage limit at 10 volts and the current limit at 1.1 amps. The auto setting was turned on so that Capstone could automatically detect the sensors. Once everything was connected, we linked both the voltage and current sensors to the Pascal interference. If the Capstone software, we changed in the Capstone software, we changed the displays to digits view so we could see the exact numerical readings of voltage and current at the same time. This made it much easier to get consistent measurements compared to using a fluctuating graph. We then measured one component at a time. For example, to measure R1, we placed the current sensor in series with it and the voltage sensor across it. Recorded data for about 2 seconds and stopped once the reading stabilized. We repeated this process for R2, R3, and R4, and finally measured the total voltage across the power source. So between each measurement, we re-zero the sensors to remove any offset error, and we double checked that the wires were snug in the breadboard so we wouldn't introduce extra resistance. After all the data was collected, we had a complete set of voltage and current values for every resistor, and using those we verified both of Kirchhoff's rules, the junction rule by comparing the total current entering and leaving the node, and the loop rules by checking whether the voltage rise from the battery equaled the sum of the voltage drops around each loop. So overall, the procedure gave us reliable data that we could analyze later to see how closely our circuit followed theoretical prediction. Here we have the data that we collected from the experiment after building the Kirchhoff circuit. So starting with R1, the voltage across it was 3.02 volts, and the current flowing through it was 0.0188 amps. For R2, the voltage was 1.2 volts with the current of 0.012 amps, and for R3, the voltage was 1.82 volts, also carrying the same 0.012 amps. Since R2 and R3 are connected in series and share the same current. So moving on to R4, we measured a voltage drop of 3.97 volts with a total current of 0.0306 amps flowing through it. Lastly, the total voltage from the source or the power supply was about 7.01 volts. These values make sense when we look at the setup of the circuit. The current is highest through R4 because it carries the total current from both branches after they rejoin, while R2 and R3 have a lower current since they split the path with R1. The voltages also add up nicely and give us a good base to test Kirchhoff's rule. Moving on to data analysis, now let's analyze the data to see if it supports Kirchhoff's rules. Starting with the junction rule, which states that the total current entering a junction equals the total current leaving it. In our case, we added the current from R1 and R3, that's 0.0188 plus 0.012, which equals 0.0308 amps. The current through R4 was measured at 0.0306 amps, giving us a percentage difference of only 0.65%. And that's a really small difference, so it confirms that the current entering and leaving the junction is essentially the same. Next, the first loop rule says that the total voltage rises from the battery should equal the sum of the total of the voltage drops around that loop. When we compare the battery's voltage, 7.01 volts, to the sum of 3.02 plus 3.97, we get 6.99 volts, which gives us just a 0.29% difference. That's another strong confirmation that energy is conserved within that loop. Finally, we tested the second loop rule, which compares the voltage across R1 to the combined voltages of R2 and R3, since those are in series. And when we add 1.2 and 1.82, we get 3.02 volts, exactly matching the voltage across R1 for a 0.00% difference. So overall, all our percentage differences were well under 1%, and that means Kirchhoff's junction rule and both loop rules are completely valid based on our data. These results show that the electric charge and energy are conserved, and that our experimental setup from the wiring to the sensors worked exactly as it should have. And even with tiny measurement variations, the theory matched the experiment almost perfectly. Moving on to the conclusion, now that we've gone through the data and all the math, let's talk about what it actually means. So in this lab, we set out to verify Kirchhoff's rules, and the data clearly supports both of them. The junction rule told us that the total current entering a junction equals the total current leaving it. When we add up the current from R1 and R3, we got 0.0308 amps, which was almost identical to the 0.0306 amps flowing through R4. That's only about a 0.6% difference, which is incredibly close. It proves that electric charge is conserved and no current is mysteriously disappearing in our circuit. the loop rules were just as accurate. When we compare the total voltage from the source to the sum of the voltage drops across R1 and R4, we got a difference of only about 0.3%. And in the second loop, the voltage across R1 matched the combined voltages of R2 and R3 exactly. This shows that energy in an electrical circuit is perfectly accounted for. All the energy supplied by the source is used up across the resistors. Our results didn't just confirm Kirchhoff's equation on paper, they actually showed how these conservation laws look in real life. Every little reading and every stable digit on the screen was essentially a snapshot of charge and energy behaving predictably. And that's something we usually only imagine when we're solving problems on paper, but seeing it play out in the lab was pretty satisfying. So, of course, like any experiment, there were small sources of error. A few possible reasons for those tiny differences include calibration drift in the sensors, resistance in the breadboard connections, or even the wires themselves adding a small amount of resistance. The Pascal current sensor also introduces a little interval resistance, which can slightly change the true current values. And to minimize those issues in the future labs, we could re-zero the sensors before every measurement, shorten the wire links, and make sure all the connections are tight and clean. It might also help to take longer recordings, maybe 5 seconds instead of 2, to make sure the readings are stable before saving them. Overall, the fact that our percent errors were all under 1% tells us that our setup was solid and that Kirchhoff's law really do hold up under experimental conditions. So, and this wasn't just about verifying equations, it was about seeing the conservation of energy and charge in action. And that's one of the coolest things about physics, even though I do not like